So hello everyone, welcome to the second lecture of these RISC-V classes. Just a reminder, this class was yesterday, today, not tomorrow, Thursday and Friday. So tomorrow there's a poster session, so there won't be a third lecture. So, for those of you that were here yesterday, just a recap of what we've been discussing. We discussed about what edge devices are. So we say that they are different from, for example, the CPUs that you have on your own laptop, that they are different than the ones on servers or in your cars and so on. They are those CPUs that are, or system on chips that are close to the sensors and that they process data that are actually gathered nearby. We discussed how the edge device should look like. For example, we said it should be programmable, versatile, because you don't have a fixed application, you have a domain of applications that you want to deploy on your hardware. And we said that they are battery powered. That means you don't have a lot of power to use for your own computations. You're not plugged to the electricity or so on. You have usually a few milliwatt as maximum power budgets, and also you have limited energy. So you want to both consume low power, being small because you are embedded in those sensors or close to the sensors, and energy efficiency. Then we said how to achieve energy efficiency. The answer was depends, exactly. Depends on the workload you're trying to run. And, but usually what is efficient to do is doing domain specialization. So domain specialization means you're adding acceleration, either in software, in hardware, in both, at application level or at deployment level or whatever. That makes your system either faster or more energy efficient or consuming lower power and so on and so forth. We made some examples. Some of you suggested let's use clock gating, power gating to reduce the power. That is a generic optimization that is always good to have, and it's usually domain independent. Then there are other optimizations that are domain dependent. So for example, adding extensions, customization, accelerators for those functionalities that you want to be good at. For example, FFT, security, and whatever else. And to conclude, because we said we wanted to have this system programmable, we said that it's good to have processors inside. And for those processors, we chose RISC-V because it's modular, extendable, and free to use, open source. And we described what RISC-V is. And we concluded by saying that the ISA is not the implementation. And we made a few examples. So starting from this last point, so the ISA is not the implementation, today we discuss about the implementation. So yesterday we discussed about the ISA. Okay, so first of all, how many of you has ever designed a CPU in general? Or, wow, a lot of CPU designers. What were the ISAs that you were, let's say, mostly using? Probably MIPS. Will it be the case? How many MIPS? Me too, actually, when I was the master. Otherwise, RISC-V, yeah, of course. There's Open RISC, also open. I actually extended an Open RISC core during my master's thesis. Others? No? Okay, good. Was just for me to know. Okay, there's something broken with the slides there, but yeah. You remember that we said depends. Right? How to achieve energy efficiency depends. So we start from here. We have an application that is doing, for example, while one. This is very typical in embedded systems. Usually you are sleeping or you are waiting for something happening. Hopefully during the sleep time you're actually consuming very little power. Maybe you are in deep sleep state, whatever your embedded system allows you to do. Then you get an interrupt, an event that could come from a timer if you are timely getting data from outside, or maybe you get a GPIO triggering from another device and so on. You wake up, you jump to the starting of your transfers of data coming from sensors. Maybe you have an ADC, so you're taking them on chip and so on. And once you're done, what you usually do is post-processing those data, or pre-processing, depending on your point of view. For example, you're doing a feed filter, you can do the FFT, it can be the whole neural network, it can be whatever is encryption, decryption, whatever you're doing, okay? So if you want to design a very energy efficient CPU for this guy, or a very energy efficient CPU for the other task, so the FFT, will this CPU be exactly the same? And what would you change between the two? I didn't hear.
I will give more L to the FFT one for sure if it's like an out-of-order execution.
So you want to give more area? That's what. Okay, LEUs. Okay. So you want to give more, data path to the CPU doing FFT. Okay. Then you mentioned out of order. So maybe the architecture, the computer architecture of the CPU is performance oriented, or yeah. So you will select an ISA among the ones that we saw yesterday, different between the two. Good. So you will select, for example, the vector extensions on the core running the FFT.
Probably needs a floating point of a double.
Yeah, another extensions could be the floating point or double precision RISC-V extensions on the, I guess, on the FFT CPU.
And DSP, an accelerator for FFT.
Okay, so you will add an accelerators or a DSP extensions or a DSP CPU to the, you will use actually a DSP CPU for doing the FFT. No one is talking about this guy?
I would probably not have floating point on the control.
Yeah, for example, this guy won't have the floating point unit then?
We might even like remove some registers on the 16 on the control if it's sufficient.
Exactly, you can use the RVE extensions on RISC-V, still within the RISC-V context. So having less registers here.
We can have a very small data path for the ALU. If we don't do any computation, why not take many cycles?
Exactly. Yeah. For example, here we can have an addition done in 5 cycles, 4 cycles, 8 cycles, whatever. Because who cares? We are doing very little additions on this side of the task, right? I mean, this is C code. It's probably full of additions because of creating addresses and so on. But yeah, that too. Yeah. You're done. Okay. So you see that if you have a single CPU, cannot be efficient in both, right? And why that CPU is not energy efficient, so energy, not performance, when running this task? What is it? What are you wasting? So I want to use the CPU you suggested me to use for the task 1, so the FFT, to run the main loop. Why is it not efficient?
Because we will have more standard cells, so more static power consumption.
Okay, more leakage power.
If it's out of order and you get like extra performance from that, that doesn't matter much if you're just spending most of the time sleeping anyways.
Yeah, so so similar to the, probably similar to your colleague's explanation. So you're wasting leakage power. Although in sleep mode, theoretically, you can also power gate, right? So in that case, you won't consume any leakage power, but you consume area. So your chip is more expensive, but you don't really need to make it that big, right? Otherwise, yeah, but those are pretty much the reasons. Okay, so now we see a few of CPUs that are open source. So it means that you can Google them, they are on GitHub, and they've been optimized and designed exactly for these two different profiles. Of course, when you build your own system on chip, as your colleague, one of you guys, I don't recall who, suggested yesterday, you have to profile, right? So you have to understand exactly what are the set of applications your system on chip is going to run. If you are doing a system on chip and most of the time you have a dedicated accelerator to do data processing and your CPU is only there to do the task here on the left, so it's controlling, orchestrating the SoC because the computation is done by the accelerator, then you want to go for this kind of CPU for your system. Whereas if you are trying to do both these tasks and the computations on the same CPU because you don't have an accelerator, or because you want to have a cheaper system on chip, easier, smaller, whatever the reason is, then of course within the profile you have also to include that task. So it happens quite often that you use the other CPU for this kind of task. It's completely normal, so it's not a mistake. It's just that you have a single CPU that needs to be good in your most critical part of the design. So of course it will be over-designed for the tasks that are simpler, and here comes to help clock gating, power gating to mitigate the overheads. Okay, so of course now we learned the title of this slide. With the discussion that we just did, we say that ideally we have a core, for each workload that we need to run, we have a different core. Very important to remember, ideally, because it's not very often the case, for the reasons I just explained. But if you're building an heterogeneous system and there exist commercial products that are actually having heterogeneous CPUs running in either one or the second one for the task you're trying to do, then you may want to have more than a CPU tailored or optimized for the workload you have in mind. Okay, so we start from the tiny one. So if you are designing a system on chip and you want to have it based on RISC-V, why redesigning your own core? You can, as an exercise, or for educational reasons. But if you just need to have a single CPU ready to be plugged in your system, and I heard some of you guys mentioning this, I have to design a new system, my supervisor told me it would be nice to have a CPU based on RISC-V next to it, I think it was you, or someone else wants to play with RISC-V and so on. This guy is open source. This guy is open source, free to use, with permissive license. Permissive means you can take it, use it, modify it. You don't have to open source it back again. It's not GPL. You can do whatever you like, whether it's a research paper or it's a product. No one cares. So that is free to use. I invite you to actually go there, and you can also actually use it to learn how the CPUs are written, for example. It's not the way it's written. It's one example on how a CPU can be written. This one is written in System Verilog, and all the CPUs I'm showing you today are written in System Verilog, but there exists also open source CPUs written, for example, in Chisel. I don't know if you're familiar with Chisel, which is a Scala library which is built on Java. But yeah, Verilog and System Verilog together with VHDL are the standard, let's say, languages to describe hardware. So this has been designed at ETH Zurich by me during my PhD, almost 7 years ago, something like that. Has been optimized exactly for the task we mentioned at the beginning. So waiting for an interrupt to arrive, to then wake up either an accelerator or the transaction of I/O, and then going back to sleep again. That was exactly my context, my spec. Let's do a CPU that is good in doing that. And so to do that, as many of you suggested today, leakage power. Leakage power is important. right? Because you say, if you are over-designing your CPU, you are consuming power, but we are not actually leveraging this data path and these extra gates. So one of my main goals was designing the core to be small. How to make it small? Of course, you reduce all the possible extensions that you don't need. Someone suggests remove the floating point unit. Thanks, I did it. Don't add the vector extensions. I haven't. Don't do this and that. Someone else suggested do multi-cycles operations. Thanks a lot, indeed. This is the philosophy used to design the CPU. Then, as we said yesterday, adding C extensions will makes the CPU bigger, right? Because I have to decode more instructions. So shall I add it or not?
Depends of the memory footprint.
Yeah, exactly. Thanks a lot. So the answer of your colleague was depends. Yeah, actually it's better to compress the code, because if your code is big and you save 30%, you save SRAM area. So yes, I had the compress extensions. But those are parameters that you can plug and play. You know, you don't have necessarily a fixed single design with no parameters, so you can decide whether to have 16 registers or 32. Someone suggested use 16 registers. Yeah, that's what we did. And to have or not the multiplier and the divider in the ISA. So like this, you have 2 parameters, 4 possible cores, if I'm not wrong. And that makes an IP that can be configured in 4 different ways, that then you can select depending on the profile, knowing that the design philosophy behind was a wake-up core, you know, a guy waiting for an interrupt. Then we demonstrated the CPU, we published the paper and so on, has been implemented in Silicon several times. And then of course there were, not of course, but we were lucky because companies were interested in the core. And so, you know, in a university, if you are all PhD students like I was, you don't do documentation, verification, answer bug support, 24-hour support and so on. So you are not a company. So if you really want this guy to be pushed into products and, you know, to be used as a real product, you need a company doing that, right? So the first one approaching was the Low Risk Non-for-Profit Foundation that I guess I mentioned yesterday. So we donated the core to them. They renamed it in IBEX. So if you now look for this core, you browse for IBEX. That was not the original name. And then it has been documented, it has been verified, so it should be bug-free, and has also been extended for their own purpose with parameters, so security, for side-channel attacks, bit manipulation extensions that I didn't mention yesterday, but is yet another modular ISA extensions that you can add, good in manipulating single bits in a word. And so on. So it has been added a parametric third pipeline stage. We will see later why, and so on. And a few months later, the Open Hardware Foundation also for the CPU to bring it back to its original intention, which was small, only 2 pipeline stages, only very close to the CPU I'm just describing here, but again, verified, documented, maintained, using European projects, products, and so on and so forth. Okay, so this is an example. So for those of you that followed the RISC-V extra session at 6 p.m., this is an example of how actually influence the RISC-V community. You actually do in your research a CPU, a RISC-V core, or whatever you guys are doing. The ISA is open source. If your design is open source, it can attract companies or other universities to use it, and it can become, you know, useful to every one of you. So open source is important, and it's really something that if you can do and you are willing to do, it's actually good for the whole community. And then it gets cited a lot because it's there, it can be used, and so on and so forth. Going back to technical, what we are going to do today is looking a bit on the pipeline. Of course, I'm not going to read the Verilog line by line and explaining you how the CPU is designed, but the idea is that we, in case you are using it or extending it or modifying it, or you just are curious about the design strategies, you can understand more or less how things have been designed. So as you see, from the graph here is the CPU gets from left to right. There's a prefetch buffer. Do you know, guys, why there's a prefetch buffer on a CPU?
If there's only one memory, you can only do one memory access per cycle. So if you have a prefetch buffer, you can actually do a load and not have to stall for the next memory instruction fetch.
Yeah, it's not just the stall, it's to mitigate in case the pipeline stages in front of you are stalling, rather than the memory itself. The memory could be fast, right? Could answer in one cycle. But if you are waiting for other instructions to finish, or if you have a cache miss, then if you have something in your buffer, in your prefetch buffer, you can, recover a bit the IPC, the instruction per cycle, the performance. Okay? Then there is an aligner and a compressed decoder. Do you know why, guys? But you design CPU core, so you don't answer. Someone else?
You're only using half the word if it's a 32-bit word and you have 16-bit instructions.
Correct, exactly. If you are mixing 32-bit and 16-bit instructions, can happen that if they are only 32, for sure the addresses will be 0, 4, 8, 12, 16, and so on. They're multiple of 4, right? 32 bits, 4 bytes. So in the bytes, they are all word aligned or 32-bit aligned. But if you are mixing them, if, for example, I have an instruction at the address 12, and the next one is compressed, so it will start at 16, and the next one will start at 18. Because it's only 2 bytes. So when we fetch a word from the memory, 32-bit, we don't know if the instruction is starting at the bit 0 or at the bit 16. We don't know it. Correct? Could be that the first part is the second half of the previous instruction, or the first half is the instruction itself, the whole instructions, because it's compressed, or if it's the whole 32-bit instructions. You don't know that.
So are 32-bit instructions allowed to start at the non-4-byte offset?
Absolutely, yes. Otherwise, you won't have any advantage, right? Because otherwise you waste. It's true that they are compressed, but then you waste 2 bytes. So it will be the same, right? So yes. So this complicates your pipeline.
So sorry, you can start using compressed instruction like in line with the other instruction. You don't need a signal
No, it's done on the flight, because you fetch an instruction. So the question is like, can I have an instruction starting? Do I need to tell the CPU that I'm going to to fetch compressed instructions? The answer is no. Who knows that? No one knows, right? The memory doesn't know what the content is. So when you fetch an instructions, you just you will figure.
Of course, but to tell it to interpret it as I guess you can put in memory through, depending on the encoding, I could interpret.
Yes, depending on the encoding, exactly. But you know it once it's fetched, because it's at that time that you know the content of the memory, right? It's
so uncompressed instruction, like the first 7 bits.
Yes.
Tell you already if it is a compressed or non-compressed instruction.
Even better, the first 2 bits.
Okay.
But yes, within the 7 bits, the first 2 bits tell you that, but you know it only once you receive the data.
No, yeah, of course.
Plus, you need to have a state machine, you need states to know whether this is, the first 2 bits are the last 16 of the previous instructions, so they are not the bits 0 and 1, they are the bits 16 and 17 of the previous instructions.
Like UTF-8 for Unicode.
A bit of?
Like UTF-8, the Unicode encoding.
I don't know the specific encoding, but you need a state, yes. You need to remember what you fetched before. So for example, if you design a system, you should specify at the same time at least the first instruction. The first one, because you need the state to be in a specific state, right? Is it going to be aligned or not aligned? And of course, the usual answer is, I'm starting assuming the first instruction is word aligned. Okay, it's not that you fetch the first instruction and you say, this is the second part of an existing previous instructions. Could be compressed, but should be word aligned. It's not mandatory though, but.
So you say that you only need 2 bits to see if what you're looking at is 32-bit or 16-bit?
Not only 2 bits, 2 bits and a state to remember.
Okay. But if I have like jumped to a place,
yeah.
I'm kind of starting fresh. But 2 bits means among all like possible instruction encodings, is it 50% of them are set aside for compressed, or 25%, or 75%? There has to be like, if you only need 2 bits to decide, then you are really like splitting the possible instruction encodings.
Yes, correct.
Quite nicely. Do you know if it's 50% or 25 or 75?
Usually the amount of instructions RISC-V can compress, so that the ones that are the most popular, I would say, in whatever benchmarks they used, it's around, the code size is 30% and the number of instructions is around 50%. Something like that. I don't know how they did the statistics, but there's a paper out there that you can Google and read, which is the compressed instruction PDF.
Since we are on this topic, can you have custom compressed instructions?
I don't recall by heart. I think I did it myself, but I don't know if I was allowed to. But I guess you can. I think you can. Allowed to mean, of course you are allowed to, because the spec is open. What I mean is that whether it's compliant. Do you know that you play with custom extension?
The four custom codes are services.
Okay. So basically, the answer is both, yes and no. So, as your colleague suggested, RISC-V defines some opcodes that can be used for custom extensions. Those are there, never be touched. But once you decide what your ISA is in your CPU, you can use whatever bits, right? To implement your custom extensions. Of course, you don't have to collide with whatever else you're implementing there. That needs to be compliant with RISC-V if you call your core RISC-V. But then you can use the remaining bits to do whatever you like, right? If the custom space is not big enough for you, you can use also the rest. But I would say it's not standard. It's a bit hacky, but you can. Okay, so we looking at the CPU, we already figured out that there's a prefetch buffer for the reason we said before. There's an aligner that records the states and tell us whether it's a compressed instructions or not and where it starts from. And then that's a design decision. You don't have to do like that. Actually, I played with this parameter as well. Then the 16 bits only instructions gets expanded to 32. As you recall yesterday, I told you the RVC instructions, so the compressed ones, don't define new instructions, simply compressed existing ones. That means that for each of them exists the same instructions in 32-bit. NOP 16, NOP 32. You may laugh that NOP is an example, but actually NOP is one of them. And this is important so in my case, what we are doing is if the instruction is compressed, and I know because I have the aligner there, what I give to the next pipeline stage is its uncompressed version, such that the decoder that we will see later in the next pipeline stage only deals with 32 instructions. It doesn't need to do is it 16 or 32, because if it is 16 or 32, has been done the cycle before, in the previous pipeline stage. Is it a good thing to do here, or shall I do it in the next pipeline stages? We balanced the pipeline, the timing of the pipeline, and we figured out that it was better to do it before. Again, design choice. You don't have to do like that. Then keep on going towards the right. There's a decoder. The decoder decodes the instructions. It checks whether it's an RVI instruction or E, understands what the registers are. Are you using the register 1, 2, 3 or 5, 6, 7, whatever? it decides whether there is an addition, a multiplication, or whatever else, whatever we saw yesterday from the RISC-V ISA topic. So there is a big switch case, a very big switch case, that for each of the thing decides what to do, and then the default case, so if none of them matches, it's an illegal instruction. If it is an illegal instruction, then the CPU traps to the illegal instruction routine. That some of you suggested to use it to implement a software-based multiplier yesterday, for example, or you simply, you flood it to the operating system or whoever is running your CPU on, and that's it. Then what it does is, if it is an addition, it gives the operands and the commands to the LAU. If it is a memory operation, to the load and store unit. If it is a multiplication, it goes to the multiplication unit, and so on and so forth. So this is a simplified pipeline view, which is exactly summarizing what I said. What I didn't say before is, or maybe I did and I forgot, it's 2 pipeline stages, very, very small. So you remember the goal was low area, okay, low area. So I can save on the number of pipeline stages. Pipeline stages means registers. Registers are expensive, both in area and in power. Of course, they allowed me to go faster, to have an higher IPC, and so on and so forth. Do I need that for my wait for interrupt application? Absolutely not. So that means that if you have an instruction that requires more than 1 pipeline stage to, to keep a throughput equal to 1, will stall. And it becomes a multi-cycle instructions. A typical example of this kind of operation is a load and store. Because usually, memories are implemented in SRAM, and usually SRAM replies at least 1 cycle after. So that means that if I send the address at time t, I get the answer, best case, at t+1. So if in my ID stage I have a load instructions, I send the address now, I stall the pipeline, I cannot get another instruction to execute after because I still didn't finish the previous one. So I waste 1 cycle with a bubble, which is called in computer architecture a bubble, and then I get the answer. This is a structural hazard. Okay? Can I have data hazards in this pipeline? If any of you is familiar with data hazards, I guess, no? From computer architecture. Can an instruction in the ID stage depend on another instructions that is in the which stage? X? I don't know. Right? But there's nothing. So there's no data hazard in this CPU. Amazing. We simplified a lot of multiplexers and a lot of control state machines. Good for my area and my number of gates. But I have a lot of structural hazard, yes. But I know them at decoder time, at decoding time. I know it. It's a lot. For sure I'm going to stall at least 1 cycle. 100%. I know it by design. Is it a branch instruction? Again, I can theoretically do it in a single cycle, right? I read the registers, I decide if A greater than B, and then I use another adder to do program counter plus the target I need to branch to. Perfect. I know the address where to go. I know whether to go or not. If the branch is taken, I can do it in a single cycle, correct? How many adders do I need? As adder, I also mean comparators, it's the same. A comparator is A minus B, and then you check the most significant bit. How many adders do I need? 2. Expensive. I use 1. How many cycles do I take to branch? At 2, exactly, at least 2. The first one, I know whether to branch or not. And then the second cycle, I calculate where to branch, in case I need to branch. So that's why I'm scheduling them like this, because if I don't have to branch, I don't do it, right? And I continue with the next instruction, and I don't lose cycles at all. So non-taken branches are good for me. They don't waste APC. Taken branches, very bad. I waste 2 cycles. I'm betting on that. Is it good or not? No idea. But it's smaller. This implementation is smaller, consume less power. My goal is not performance, right? If I waste one cycle on a branch that I run 1% of my time, because most of the time I'm sleeping, I don't really care, right? Again, multiplication, similar story. So, this is the LAU. So if you go to CV2 GitHub URL, and you go to RTL, if I well recall the structure, and you go to CV2_LAU.sv, that is more or less SV because it's system Verilog. This is more or less the architecture you should expect by reading the system Verilog. So as you see, there's a single adder that is shared across many other stuff. For example, LAU operations, comparison, subtractions, additions, and so on and so forth. Branches, as we just said. But also the address generation unit. For example, when in RISC-V, I have to load from an address that is an immediate plus a content of a register. Who is doing this plus? The adder. Okay? And also the divider. So the divider can be implemented as consecutive subtractions. Why do I have to add another subtractor? The LAU, the same adder. Then I have a shifter and a logic unit, and or XOR, whatever. Okay? So this explains in the pipeline more or less what I was telling you before. You can, I say that in voice because honestly because I forgot I had this slide. But this is exactly explaining you the pipeline I was describing before. So when you have a load and store, can you read this graph? Have you ever played with the pipeline structure? So time goes on the y-axis towards down, and the pipeline stages are described here. Seems to be 3, but it's not 3. The first one is I'm sending the address to memory. So it's the program counter, I would say. It's the register that holds the next address. So while I'm fetching the address A+4, whatever A means, I got in the IF stage the previous answer. That was the content of the I memory of A. And I'm sending X. I know X, so it was the previous instructions to the data memory because I know it's a load. So I'm sending the address. I know SRAM executes at least one cycle after, so I stall. That's why you don't see anything moving in the IF. It's still the same, it's frozen there, and I get the data from the AMM. What is the prefetch doing? Getting A+8. So I can, in case, I can recover a bit later. In case I get stalls from the instruction bus, I have an instruction more in the prefetcher that doesn't prevent me to continue. Similar branches, I know it's a branch, I do the comparison first. In this case, it's a taken branch. So the next cycle, I need to branch where? To B, which is immediate plus program counter. Fantastic. Then I send B to the IMEM. I do the branch. In this case, the instruction in the IF stage is wasted because it's not taken. It shouldn't be executed. So it's killed. While multiplication, again, it's done in this case 3 cycles. There's also a parameter to have it in 32 cycles, so serial. But I've done a bit of profile, and multiplications are actually there also if you do control applications to calculate the address of the DMA or doing a bit of new things here and there. So in this case, the multiplication I chose by doing a few experiments that the best energy efficient point was 3 cycles. Okay, so first you do the first 12 bytes, then the mix products, and then you sum them up all together. And with a 16-bit multiplier, you can implement in 3 cycles a 32-bit multiplication, or in 4 a 64-bit multiplications. Then here is a slide of why you need a prefetcher, that we said that in the pipeline at the beginning. It is explaining you exactly where the instruction could be. And so you have between words instructions. And now we go to the next CPU. Questions so far?
I was wondering what was the trade-off to choose two pipeline stages? Personally, I saw a lot of...
Empirically. You do experiments, and so the goal was reducing the area, but still having a decent performance on the benchmark I had. So first you remove one pipeline stages, and you say, performance are still good. Let's go to 2. And performance are still good. Okay, let's keep to 2. That's it. So it's experimenting. A bit of experience and rule of thumb magicians, I would say.
Does going from 3 to 2 remove the need for like forwarding and hazard detection?
Absolutely yes. Absolutely yes. But load and source are faster, and branches are faster, and so on. So it's a trade-off again. The next CPU is instead the one you would use on the FFT side. I don't explain you the custom extensions this guy is implementing because that's the topic for tomorrow, but I give you a little bit of spoiler, I will say, of what the architecture implements. So this is, again, same story of the previous one. Actually, the previous one was born as a fork of this guy, as a GitHub fork of this guy. So this also was part of my PhD. It has been designed in my group. Then at the beginning of my PhD, I inherited the design, and I kept on maintaining it and modifying it and extending it during the PhD. What I've done during the master thesis was adding the custom extensions that I explain you tomorrow. But what is important to know is that this guy has 4 pipeline stages. Why 4, not 5 or 6? Again, empirically. You need this frequency, this area, this energy efficiency, okay? The guy, we experimented, 4 was the good number to go for. I forgot to tell, but of course it was quite obvious before. It's an in-order single issue CPU, this one as well. And differently than before, it implements only I instructions, always 32 registers, multiplications, optional floating point unit. Now it's important, as some of you suggested, but optional. So you can also disable it if you don't need. Compressed extensions and custom extensions. What are the custom extensions are DSP, packet CMD. CMD means more operands processed at the same time. It's like a vector, but within the Scala register file. I'll tell you later tomorrow. Bit manipulations, and so on and so forth. Similar story to the previous CPU. ATH, designed within the PAL project. A lot of silicon prototypes, papers, journals, open source, system Verilog, companies, open hardware. Exactly the same. Duel has been rebranded as CV3240P. So if you find all documents that are previous to the open hardware, this was referred to as RISC-V from ATH, and the previous one was zero RISC-V, because I don't have a lot of fantasy, and was smaller, so 0. Okay, this one has higher IPC than the previous one, obviously. That's computer architecture basic things. But still, I don't want to waste the resources, so wherever I could, we shared the data path. Okay? If I don't need an extra adder, I don't add it, of course. The fact that it's not optimized for area doesn't mean I need to waste it. Does the previous CPU implement clock gating on the operands going to the LAU? Any guess?
Yes, maybe.
But clock gating what? There are no registers to gate. That's why. So the registers, it's the register file itself. So the register file is clock gated, yes. But there is not another pipeline stage containing the operands, because there is no another pipeline stage. This one, yes. So if I'm not using one of those functional units, the operands there are not changing. They stay the same, reducing dynamic power, except one bit, enable. I have to tell the multiplier to don't do anything when I'm not using it. Except that bit, the other ones are gated. This one is the pipeline. So same story as before, I go faster. Similar IF stage. So you are fetching an instruction, prefetching, uncompressing the 16-bit ones, then you read the register file, you decode an instruction with the same big case statement. Of course, now it's much bigger because it has many more instructions to decode. Then I go to the third pipeline stage that was not there before, and I send the address to the memory. I don't need to stall. I can get the next instructions, which can be another load or something that doesn't have a data hazard this time, because now I can have a data hazard. If it doesn't have a data hazard, I can free up the ID stage to do, for example, an addition, a multiplication, because in the fourth pipeline stages, I'm waiting for the answer from the memory. Of course, if the memory doesn't answer, the pipeline is stalled, the whole pipeline. But that's not a structural hazard, it will be a stall from the bus. And it's not a data hazard because I wouldn't have let the multiplier or the addition or whatever go to the X stage if I depend on the results of the load, right? And of course, if there are possibilities to forward the operand, so for example, I have two additions, that the second addition depends on the result of the previous one. Once the addition finishes in the X stage, I can back forwards the operands without waiting to write it back to the register file to the next addition.
But if you go back one slide to your drawing, it has two write ports on the register file.
Yeah.
But if you have forwarding anyways, couldn't you just always write it back from the...
That's a very good look that you had here. It's because of the custom extensions. It's not because of the pipeline. So tomorrow you will see instructions that write two operands back to the register file. That's why. Thanks for noticing it. Now, similar graph than before, pipeline stages. I'll let you guys play with that, but very similar, but different performance now. So here jumps are done in the third cycle, in the third pipeline stage. So I'm wasting 2 cycles again, but for a different reason. But I let you guys play with this. Now the LAU is much more complex. Again, I'm spoiling it here a bit. You see vectoral comparator, vector adder, what is this thing? Tomorrow you will see. Why there are 2 others in cascade, tomorrow you will see. But that's the architecture, okay? I can already spoil you the reason. Fixed point, packet SIMD, bit manipulation. Those are the extensions we will see tomorrow. And some of the times I'm both loading from memory and updating the registers. So I write 2 things in the register file for this reason. Multiplier, again, what a beast. Why? Single cycle multiplication for 32-bit, but then custom extensions, MAC with subtractions, fixed point multiplication, dot product for vectors. My master thesis was super fun. This is the architecture that we designed. And finally, of course, if you look at the results, so you do the synthesis, this case is 65 nanometer, I don't recall, doesn't really matter. What I want to show you here is that, of course, what do you expect? What is the biggest CPU? Do I even have to tell? I don't think so. It's quite obvious that the second CPU I show you is the biggest. Of course, it has more instructions, more pipeline stages, more performant architecture. By how much? 2 times. How many of you would have guessed it's only 2 times bigger? But here there is no floating point unit, disclaimer. Because otherwise it's not just 2 times. But it's only 2 times bigger, and why? You see from here, the register file is big. Why it's bigger here? More read and write ports. But look at the adder, or the multiplier, or the LAU, much bigger. And if I even remove the multiplications on the side there, and I only reduce to 16 registers, you see how the register file is smaller, and there is no multiplier and divisor unit, 3.5 times smaller. Good. Now, what is the most performant core? The answer is, altogether? Oh, okay, it depends, exactly. It depends on the benchmark, on what you're running. Are you running a convolution neural network on images, what is the most performant? Of course, the second CPU, right? By 6 times with respect to I and M, or 50 times if I remove the multiplication. Why? Because this guy is only doing multiplications. If I look at mix of control and computation, still the best, right? Still the best, but by less, because now computation counts for less. It's there, still counts. You see, it's always the fastest. The blue, it's always the fastest. There's no point, it's from a design point of view. But what's the difference? That's important with respect to the others. So if I now look at the energy, before I go to the next slide, don't look at the slides. What is the most energy efficient? The answer is, but is it exactly the same graph? But why? Here I'm the fastest. Why I'm not also the most energy efficient? Because energy is time times power, right? So why, if time is the shortest, why I'm not the most energy efficient in the second column, for example? Or in the first one, maybe I'm not the most energy efficient here as well.
Well, it was 2 or 4 times larger, and your difference is less than that here in speed, right?
Yeah, but I said power, not area.
They're related, right?
Exactly, they relate. Not exactly with the same number, but they relate, yes. Exactly. So if I consume 10 times more than this guy, am I more energy efficient in doing the convolution? Because I get less times, 6 times less time, and I consume 10 times more power. Is the product better? No. So it doesn't, being faster doesn't mean being more energy efficient. It depends. It depends if my speed compensates for the increase of power. If it doesn't, I lost the bet. I lost the trade-off. In this case, yes, I'm not consuming more than 6 times, so I'm more energy efficient when I do the convolution, but I'm not when I do the core remark, because it's only 1.3 times. I'm 30% faster. Not enough to compensate the power. The other one consumes even less. It's also true the other way around. The black CPU is consuming even less than the one in the middle. But because it's much slower, again, the product is not beneficial. Because even if you consume less, but if you consume it for longer, energy is still higher, you see? And finally, if they all perform the same, the one that consumes the least is the most energy efficient. Okay, that basically concludes that specializing makes sense. If we do the relation with the MotoGP from yesterday, I told you I prefer moto than cars. This one is specialized for going fast, like MotoGP guys are doing. The other one is for power. The one in the middle, I don't know, but I have to be coherent with with the slides I presented yesterday. Okay? Last point. Well, everything I said was partially true. Why? Let's go back to this slide. Have I told you exactly the frequency of the computations I need to do? Here I wrote C code. That's it, right? Did I tell you how many times I wake up? I told you there's a timer, for example. Did I tell you how long is the timer running? No, right? Okay. If I'm a sensor and I need to be reactive and in a domain that is always on, I cannot switch off because I'm the sensor itself, for example. And of course you can do power gating only on the CPU, but power gating is expensive. It's difficult to design, takes area. Yeah? It's not always possible to do it or convenient to do it. So what do I do? Or maybe there are technologies that are not consuming a lot of leakage power. So if you do power gating, you save 1%. Very little. So it's not always a solution that you can go for. You can go for power gating only if the thing you are power gating is big relative to whatever you are doing. If it's the whole chip, what are you power gating? So if I'm on, I cannot power gate. What am I doing when I'm sleeping? I'm consuming?
Leakage current?
Leakage power, yes, leakage current. So if I do the 2D convolution, so the one that the biggest was the most performant, if the sleep is 1 microsecond, okay, those are random numbers, of course, we need to put them in perspective, but if I wake up very often with respect to the computational load, fine, right, because I'm leaking for little time. If I run every 2 hours, I leak for 2 hours, then I compute few microseconds, and then I leak for 2 hours. My deadline is 2 hours. It's not really convenient, right? So if the deadline allows you to be slower, because maybe you need to be fast because you are doing a real-time whatever. But if your real-time constraint allows you to be slightly slower, for example 6 times slower or 50 times slower, maybe this is not the most energy efficient core. Because, that's the graph, while I'm waiting, my energy in the logarithmic scale is increasing because I cannot switch off. And if I'm waiting too long, doesn't really matter the numbers that are here. Those are 65 nanometer in whatever context, whatever voltage, doesn't really matter. But there exists a point where the second CPU becomes more energy efficient because it's leaking less. It's true that finished later. You see it finished here. And the black dots are the graph before. So this is 6 times. See, if you do this, it's 6 times faster. And the energy is worse, because you see it's more energy. So it finished later and consume more energy. Fantastic. Now I'm waiting. This guy is increasing leakage much faster than the other. And so, in this specific case, 650 milliseconds, the second CPU becomes better. Even more, if you wait 31 seconds, it doesn't really matter, but if you wait long enough, the third CPU that you wouldn't have given a single hop from the slides before becomes the most energy efficient. And if I do a serial CPU that gets 32 cycles for every instruction it does, there exists a point maybe in 3 minutes on the X scale, that becomes also more energy efficient. Of course, you can do it only if your deadline is before those numbers. But if that is the case, careful in saying this is the most energy efficient. As you see, there is no linear formula to say this is the most energy efficient solution. So when you go home, you will always say depends. But now you can articulate a little bit more, hopefully.
But here there are same frequencies.
Yeah, same frequency. Yeah, of course. The CPU, I didn't say, have been designed to meet the same frequency. So the balancing and the pipeline stages have always been checked to have the same frequency. Why? Because they operate in the same system on chip. And I don't want to slow down the whole system because of one IP. I want to have the system balanced.
Is the black line the IMC or the EC?
EC.
But it says the red line in the top.
The red one is the IMC.
Okay, but if you look at the top...
It's a mistake, thanks a lot. It's wrong.
Yeah.
It's wrong. The bigger characters are the ones that I checked better, and they are correct. Thanks, you can fix actually your slides. Cool. Concluding, I heard by many of you guys that are doing custom extensions, as the gentleman here. How are you implementing the custom extensions?
I implemented a co-processor in the CV6.
In the CV6? You're using the X interface?
Yeah.
Yes, okay, perfect. So you know the topic that I'm about to introduce.
I also added it as another
LAU, okay, perfect. So how to extend an existing CPU? As I told you, these 2 CPUs are open source, right? So now you go home, you clone them, you clone them from GitHub, you modify them, and you want to add a new instructions, which is counting the number of 1 in a word, for example, which exists already, but let's say. How do you do it? CPU designers, how do you do it? Step 1, Please, guys, I don't know how to do it.
You need to know that decode it somehow, right?
Yes. First thing, you select an empty space to tell the CPU, when you meet this sequence of 1 and 0s, that means I'm counting the ones in a word. Fantastic. And you decide which field has the register for the destination, source. You define whatever you like based on the lecture we did yesterday. Then, where do I add this thing? In the? Before. Into the? Into the decoder. So you modify the switch case. Then you create new signals that go to the data path. And into the data path, what do you do? Yeah, you build, for example, the other tree counting the number of ones. Perfect. Does it work? Yes. Perfect. Now, who is maintaining this new CPU? Is it open hardware? You go home and you modify Linux. Do you think Ubuntu is knocking at your door, helping you fixing the bug that you are introducing or features that you are modifying in your own room? No. And we are not doing the same with the RISC-V or CV40P. So who is maintaining the CPU? You, right? So to not do that, and you have a colleague that is already experienced with that, we wanted to have an extensions to the CPU, a new bus, where you can plug your coprocessor such that the CPU remains the same. And if it gets updated, you can update the CPU as well, because you are adding things external to the CPU. So how to do it? Anyone has any idea? How to do that? So we have to do the same things as before, but now we have to do it externally. So how do we do it? But what do we communicate? Yes, we offload the instruction. So we fetch an instruction, we don't know it, so we want to jump to an illegal routine, but we don't do it because we know there is an external bus. So we give the instruction to the external bus, there's an handshake, and I ask the coprocessor, is it your instructions or not? If not, then it's an illegal one and I trap. If yes, deal with that. I can help you, I can give you the operands of the register file, you can give me back the results such that I write back to the register file, and so on and so forth. But the data path and the decoding, I don't do it. If I don't do it, you do it in your coprocessor, and you now only maintain that part. It's still your business, but it's smaller. And decouples the two designs. Does it work in all the possible instructions and exotic cases? Absolutely not. But for standard, let's say, data path only instructions, it works quite decently. And that's what we did within Open Hardware. So this is another CPU, which is a fork of the E40P, that's why they have a very similar name, where we added also the possibility of having 16 registers, the possibility of removing the divider. I don't know who asked me yesterday, can I remove the divider within the multiplier? Yes, you can, and we implemented it here. There are also atomic instructions, and there is an X bus, where X is whatever custom extensions. Whatever custom extensions, whatever illegal instructions gets offloaded. Gets offloaded where? To a coprocessor that is outside, that is receiving the instructions. It's implementing the slave side of the protocol. So the CPU is the master, and it gives you the instruction. It starts the translation, and then you reply yes, no. Yes, it's mine, granted, or no, it's not mine, trap. Then you do whatever you have to do, and then you reply back with the results of your instruction. Question?
But you do give it like registers and stuff?
Yeah, you give the operands, yes.
After that part, okay.
Yes. So the question is, do I need to give out also the operands or just the instruction? Yes, if you read the register file, you need to read the content, right? So, similar pipeline than before. As I told you, it's a fork of the same CPU, so things didn't change too much. But now, you can even do more pipeline stages, right? I don't really care what the coprocessor is. Can be an out-of-order machine. I don't care. I care that you respect the protocol, I give you an instruction, and you give me back the result sooner or later. That's it. Now, the sooner or later depends on the CPU. If I'm an out of order, if this guy is also out of order, then you can reply whenever you like, and I continue doing stuff. If this guy is in order, then I wait you to finish your instructions, and then I commit. That's implementation dependent, not protocol dependent. So that depends. In this case, the CPU is in order, but on the X interface can speculate a bit. It's a mix. It's in order, but it's tricking a bit, and it's waiting you to finish without stalling the pipeline. Okay. Magically in time, I don't know how, but we are done for today. What we take home is that yesterday we saw the RISC-V spec. Today we saw examples of implementations. There are many others out there that I invite you to have a look at. The most famous one from Berkeley, the originator of RISC-V, is the Rocket Chip and Chipyard that are written in Chisel, so maybe you don't know Chisel. I personally know it very little, but those are open source performance CPUs. There are CVA6 that some of your colleagues mentioned. That is also from open hardware, but is application dependent, so it's not very often used at the edge for data processing. As this class is tailored at the edge, we skip that CPU, but that CPU can run Linux, has memory protections, has 6 pipeline stages, out of order, superscalar, can do many more things. Of course, it's bigger and consume more power. There are other Verilog CPUs, VHDL, blah, blah, blah. How to navigate in this forest of IPs? I don't know. It's good that there are a lot, but if you have to play with things that you want to work, then I suggest you to get them from sources that are documented, verified, using products. So do a little bit of research. Open hardware, not because I work there, but we are verifying those 2 CPUs are verified. Low risk is verifying HiPEAC. I don't work for that. The Rocket Chip is used a lot. I don't know the verification status, but it's used a lot in many tape outs and research projects. So I guess its verification or technology readiness level is quite high. And so you can play with the CPUs out there. If I forgot some, I'm sorry. But go there, play with that. That's the good of open source. There are also closed source RISC-V CPUs. Don't take home the fact that it's RISC-V, then it's open source. Absolutely not. The ISA is open. The implementation is up to you. You can build your own CPU, make a company, and sell it. There are companies doing that, by the way. Then you take home that CPUs are designed always with a target in mind. Whoever designed my Intel i7 didn't do it for awaiting an interrupt for an ADC triggering every second, right? It would be not the smartest design choice. And vice versa, right? So knowing the context and what you're going to do is key. This we said that yesterday, we repeat it today. And we saw examples of doing that. How to achieve domain specialization, custom extensions. We will talk about it a lot tomorrow, and not tomorrow, Thursday, and even more on Friday with accelerators. But to do that, you need to extend the ISA if you're adding new instructions. How? Either you modify the pipeline, as we did in the E40P. So the custom extensions are there. That's why you saw vectorial adder, vectorial comparator. Those are inside the CPU. Or to decouple the CPU from the ISA extensions, you can do it offline with another coprocessor with the X interface. There are trade-offs, but definitely it's easier to do it if you do it outside. Questions? Okay, then we see each other on Thursday. Thanks.